Hello again. This is alternative delivery for Math 1120 for April 7th, 2020. Please have pencil and paper and the notes that I posted in Blackboard near at hand, maybe making some additional notes, and make sure to pause and rewind and replay the video to make sure your learning is as deep as it can be. We're going to start by reviewing the objectives that dealt with grouped data and weighted means. Now these are the formulas in your book to get the approximate mean of a variable from a frequency distribution. Now in a frequency distribution, often you have a value that represents the midpoint for a class, but you don't have individual values, but you do have counts on how many things fell into the class. So if it's a population, you take each class value times the frequency it occurs, divide by the summation, which is the total number of observations that you have. You do the same thing if it is a sample mean, and that is x bar, so that is the formula. There's a related concept called the weighted mean, x bar sub w, and what you do here is you have different weights that you assign to each of these classes. So w1 times x1, w2 times x2, so on and so forth, and you divide by the summation of the weights. And so wi is the weight associated with the ith observation, and xi is the value of the ith observation. Now a great example of this is your grade point average. So here you have a student named Marissa who's just completed her second semester in college. She got a B in her 5-hour calculus course, an A in her 3-hour social work course, an A in her 4-hour biology course, and a C in her 3-hour American Lit course. She has total value points the same as the college user page has. We want to determine her grade point average. This is a weighted average problem. So please hit pause now. Let's see how you did. So the number you should get is 3.27. You multiply each grade by the number of credit hours. Those are the weights. We can also approximate the standard deviation of a variable from a frequency distribution, and works pretty much the same way. The formulas, of course, are different. We have xi as the midpoint, thus representing the ith class, and f sub I is the frequency of the ith class. So you have these formulas. This is for a population standard deviation. You divide by the summation of the frequencies. And this is a sample standard deviation. You divide by the summation of the frequencies and subtract 1. Now, an algebraically equivalent formula for the population standard deviation is shown here. And in fact, this is the formula that many of my engineering students really like. So let's look at a problem then. This has the birth weights of babies. We have frequency table and we have cells. So we need to calculate the mean and standard deviation birth weight. Please hit pause and give it a go. Let's see how you did. All right, so here are the tables like they are in your books, and here are the formulas that we use. Notice we're using the shortcut formula here. And so we get the mean is 3,281.5 grams, and the standard deviation is 648.8, again, grams. We're now transitioning to talk about normal distribution, some of the other things that you studied from the videos and also read from chapter 7 in the Sullivan book. So the area under a probability density function represents the probability of observing a value in that interval. The thing you want to really remember here is that area and probability are the same thing. You also want to remember that the total area under a probability density function is 1. We will be using that yet today. You also want to realize that the bell curve is symmetric, and this can often be exploited when you do calculations like they did in the videos. They also introduced you to a very important fact called the empirical rule. And the empirical rule says that a normal distribution looks like this. We have, and you see the symmetries that are here. But about the mean, within one standard deviation, you have about 68%. Within two standard deviations, you have about 95% rather. And within three standard deviations, you have 99.7. This is an important relationship to remember. And in fact, if something falls outside of 2 standard deviations away from the mean, we declare it to be unusual. So here's a problem dealing with gestation periods. They're representing an area here under a normal curve, and they're asking you to provide 2 interpretations of what this area means. And here's another area under the gestation curve, the normal curve, and they're also asking you to give 2 interpretations of that. So please hit pause, think about it, and let's see how you do. Let's see how you did. Well, so the interpretations are in part A, the proportion of human pregnancies that last more than 280 days is about 19%. Interpretation 2 is the probability is 0.1908 that a randomly selected human pregnancy lasts more than 280 days. And the same thing actually happens with B, except here the probabilities are between, or the proportions are between 230 and 260 days. One of the things that's going to be important in doing these normal calculations, as you recall from your from the videos I asked you to watch, was that we have a standard score, or do we do standardizing? And this basically is changing a number so that we know for observation X, how many standard deviations is it away from the mean. And so this is called a z transform at z equals x minus mu over sigma, and you'll see that we use this over and over again. If the mean is 0 and the standard deviation is 1, we call that the standard normal distribution, and that's what the table in your books are based upon. So we have 2 spaces. The x space, which is normally distributed with mean mu and standard deviation sigma, and this always represents what I call the real world. The other space you have is called the z space, and this is the table in the back of your book. And this is a normal with mean 0 and standard deviation 1. These 2 spaces are connected by, the arrow goes both ways, by a formula which is the z transform. Z is equal to x minus mu over sigma. This is an area preserving mapping, and that means that we use this to go from one space to the other. And so I said there are 2 spaces, the x space and the z space. There also are 2 great problems. One of them is given numbers, find the probabilities. The other one is given probabilities, find the numbers. We'll do some of each of these. And this is what the normal standard deviation looks like in your book. And drawing pictures for these curves can be very useful. So, and you don't have to draw a nice picture, but just a sketch can help you think about the problem. Here is the table in your book. Now this is for negative z values, and so the numbers are along the outside of the table. So for example, this is minus 3.0, and this is 9. So it is 3.09 is what number you would get there. So the numbers are on the outside of the table, probabilities are on the inside of the table, and it is important that you note that this picture reminds you that what value is being given for the probability is the area under that part of the curve. These is for negative value z. The table continues on another page for positive values of z, and again we show the area that is represented. On the bottom of this positive page, there's another insert that will be useful when we talk about confidence intervals. And so I'm mentioning that now, and we'll refer to that later, but that is here for you if and as you need it, and I will tell you that you will need it. Remember again, the numbers in a normal table are on the outside, and the probabilities are on the inside. Now here are examples of the 2 great problems. Up here we have a number like 35, and we're asked to find the probability, p. Down here we're given a percentile or a probability, and we're asked to find the number that's associated with that. So this is finding a probability given the number. This is finding the number given a probability. In both cases we're looking at a distribution that is normal, and the mean is 50, and the standard deviation is 7. Let's do some of these problems. Problem number 25 says you want to find the probability that x is less than or equal to 45. Well, that's x, so that's over here in x space. This is a normal, mean of 50, and standard deviation of 7, and x is equal to 45. This is the real world. Now, we have a table for z space, so we have to change this x value of 45 into a z value, and the way we do that is the formula. So z is equal to x minus mu all over sigma. You do the calculation, you get z is equal to minus 0.71, and you can look that up in your table. If you look that up in your table, you come down to this spot here. Make sure you can do this, and you read the number that you find, and the number that you find is 0.2389. And again, this is an example of given numbers finding the probabilities. Let's do another one. Now this one says p is greater than 35. Note that's not what your table gives you, so we're going to have to subtract this from 1 before we're finished. But again, x is going to be 35, so we'll change that into a z-score. So 35 minus 50 over 7 ends up to be minus 214,285. We look that up in the table, and this is where we're looking, and we get 0.0162. But we have to subtract that from 1 because we want the area that's bigger than that, so we get 0.9838. Again, an example of given numbers finding the probabilities. Now here's another one that I guess I would like for you to maybe think about for a moment. Here we have to have what's between these. So pause, give it a go, and then come back and we'll talk. Pause now. Let's see how you do. Well, what happens is you really have to do the problem twice. You have to figure out what is this area here, using the techniques that we had before, and then figure out what is the area here, and you subtract the two, and your answer should come out to be about 0.9074. Now let's look at the other great problem. Given probabilities, find the numbers. And in problem 34, we're talking about what is called the 90th percentile. That means that 90%, let's just talk about babies, 90% of the babies, if your baby's weight was in the 90th percentile, weigh less than your baby, and only 10% of the babies weigh more than your baby. So we want to find the 90th percentile. This is a probability. It's saying the probability that a baby weighs less is 90%. And so what we have to do is the problem, this is the second great table, given a probability, find the numbers. We go directly to the z table and we find the number that is closest to 90%. And again, we want that to be the 90%. And so we look that up, and the number that's closest to that is this one. And when I run my finger across and up, I see that that is 1.28. And so I'm going to say that's the z value I want. I want to find out what x was. So it's x minus 50 all over 7. I solve this equation. I get x is about 59. Let's do one for the 38th percentile. Again, we're looking for 0.38. We're going to be on the negative side of the z table, and we'll find ourselves here. That is going to be minus 0.31. We use the z transform to solve for x, and we find out x is 47.8. Do several of these because I'm convinced I will ask you some of this on the final later. Here is a word problem for us to look at. This is Wendy's drive-thru, and they're telling us that Wendy's drive-thru has first of all, it's normally distributed. It has a mean drive-thru of 138.5 seconds. It's normally distributed, and the standard deviation is 29 seconds. They ask you a question, what is the probability a car will get through in less than 100 seconds? What's the probability it'll take them more than 160 seconds? What fraction of the car, what proportions of the car will spend between 2 and 3 minutes? Notice that they changed the units on here, so you have to think about 120 and 180 if you're thinking about seconds. And then it asks, would it be unusual for a car to spend more than 3 minutes in the Wendy's drive-thru? Remember that 5% is the cutoff for something being unusual. And then they ask why. Pause now, give this a go, and we'll return and see how you did. Well, here are the answers that you should have gotten. 0.09216. Again, you might get a little bit different answer than that with the tables, but I'm not going to grade the last decimal point, so that's fine. For the second part, more than 160 is about 23%. Between 2 and 3 minutes is almost 2/3. And if you say how many of them have to spend more than 3 minutes, it's 7%. Now 7% is more than 5%, and so you would declare that as being not unusual. Here's another question dealing again with Wendy's drive-thru with the same statistics. Suppose that Wendy wants to institute a policy at its restaurants that it will not charge any patron that must wait more than a certain amount of time for an order. Management does not want to give away free meals to more than 1% of the patrons. What time would you recommend Wendy advertise as the maximum wait time before a free meal is awarded? Now this is the other kind of problem. It's given probability 1%. What is the number? Hit pause, work the problem, and let's see how you did. Let's see how you did. So you should have gotten, the cutoff is 206 minutes, and 206 minutes, let's see, 3 minutes would be 180 and 4 minutes would be 240, and so I'm not sure what you would recommend, but this is how you figure out what's the cutoff point there. Okay, so looking ahead then to next week, and then will be more discussion on this next week, but I have some additional videos I would like for you to watch. These are again from the Produce series on data, and it's and again they're excellent videos. This is where you find them, and these are the lessons I would like for you to look at. For next time, we're going to talk about these, and these correspond to the relation between two variables, chapter 4, and their chapter 4.1, 4.2, and 4.3. So videos to watch and pages to read. More on these next time. Now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. Take care of yourself.